Hi, good afternoon, everyone. My name is Carrie Worthington, and I am with the NARUC offices, the National Association for Regulatory Utility Commissioners. Today we have a webinar on the climate impacts of thermoelectric power generation on the Water and Thermoelectricity Energy Nexus. And we have been able to provide these webinars due to our partnership with Sandia National Laboratories and the U.S. Department of Energy, so thank you. To ensure and enable your ability to participate in today's webinar, please send questions and comments through the chat function or the questions function of the GoToWebinar platform. We will be taking questions that way. We will not be opening the phones. Today, our moderator, and I'm sorry on the screen you see it incorrectly there, but it is Commissioner Mary Anna Holden from the New Jersey Board of Public Utilities. Commissioner Holden is an active member of NARUC and is the chair of the Water Committee at this time. So, Commissioner Holden, the floor is yours.
Thank you. Well, good afternoon. This is a very important topic that we're going to discuss about the 1,080 thermoelectric plants across the United States, not each one individually, however, but we're going to be talking about considerations of the engineering interactions of the climate, hydrology, and environmental regulations. And we're going to show the potential for adaptation of future climates by capitalizing on the size of regional power systems, grid configuration, and improvements in thermal efficiencies. And joining our expert presenters today is Dr. Ariel Miara, he is a visiting scholar at the National Renewable Energy Laboratories Strategic Analysis Center. You know that better as NREL. He's been collaborating on research related to energy water issues as well as energy forecasting and modeling. And he's been working on this with Jordan Macknick. He's the lead energy, water, land analyst for NREL and member of the systems modeling team within the systems modeling and geospatial data science group. We will also have Dr. Vincent Tidwell will be adding some commentary of Sandia Labs. He's a principal member of the technical staff at the labs with 18 years of experience conducting and managing research on basic and applied projects in water resources management, among other things. So good afternoon, and Dr. Ariel Miara and Jordan Macknick, if you would like to lead it off.
Okay, thank you. If you hit the next slide, please. Thanks. So the work that I'll be speaking about today is part of a National Science Foundation project that's been going on over the past 4 years, made up of a team of different universities and national labs across the country. And our focus has been trying to understand better the connections between climate, water resources, and electricity generation. I'm going to highlight key results and messages from 3 studies that we've done and give you an idea of where the research is at now in terms of looking at climate impacts on electricity generation and the type of planning tools that we have available to look at these types of issues. And I also want to mention that we're in the final stages of this project, and one of our main goals was to engage with decision makers and get input on whether our studies and modeling tools are ready to answer key questions that regulators or energy planners and so on might be interested in asking, and partnering with them to design experiments and address some key issues related to climate impacts on electricity generation. And I'll come back to that at the end. But first, I'll give a quick background as to why this is all important, and then I'll go into the key results from the 3 studies. Next. So today's electricity generation, about 85% of it relies on cool ambient temperatures, so cool air temperatures, and sufficient volumes of water, mainly for thermoelectric cooling, and that's coal plants, nuclear plants, and even natural gas combined cycle plants. Next. So as well as requiring water for the cooling process, and whenever there isn't enough water or the temperatures are too warm, by the way, the operations of the power plants are less efficient and power production is affected. But as well as requiring water, these thermoelectric facilities also impact water resources. And the two main technologies used by thermoelectric plants for cooling are recirculating cooling, where the impact is really evaporating a lot of the water that's taken in. And that's basically releasing the waste heat from the power plant into the atmosphere through evaporation using cooling towers. And the second type of technology is once through, that takes in a lot of water, doesn't evaporate much of it at all, but it discharges that water at warmer temperatures back into the river, and that affects aquatic habitat and fish, and that thermal pollution cascades downstream. Next, please. Next. Yeah, thanks. So because power plants affect water resources, they're also regulated. There are two main types of regulation that affect power plants and their water use. The first one was creating the Clean Water Act in 1970 that puts a limit on the thermal pollution that's allowed to be discharged by power plants. And whenever river temperatures get too warm, power plants may have to curtail operations or ask for variance permits in order to continue operation. The second regulation, which is a little more recent, puts a limit on the amount of water that power plants can use for cooling. And this type of regulation has led to a transition from the once-through technologies that take in a lot of water to recirculating technologies using the cooling towers that use less water. And so over the past couple of decades, we've seen a shift in such that new power plants are using cooling towers, and there are less and less once-through power plants being operational. Next, please. So because of the interactions between climate, water, and electricity generation, over the past couple of decades, there have been several instances in which power plants have had to shut down or curtail operations when there isn't enough water for cooling, or if the water temperature is too high. And the map shows all types of incidents that have happened throughout the US. Now, most of them happen in the eastern part of the US because that's where most of our thermoelectric generation that relies on water for cooling exists, and most of our power plants exist in the Eastern Interconnection. So that's why most of the occurrences and incidents have happened there. If you go to the next slide. So understanding that there's a connection between climate, water, and impacts on electricity generation, and that electricity generation is vulnerable to changes in climate, to warmer climates, and to water stress. There have been a lot of studies that have tried to understand what is our available capacity going to look like in 10, 20, 30 years in mid-century, when the climate does warm and water stress and extreme weather events become more frequent, like heat waves. What's our available capacity going to look like? Are we going to lose a couple percent of megawatts? Is it going to be more? And what regions are more vulnerable? And so with all of this in mind, if you go to the next slide, we have three questions that we try to address through three studies that we decided on internally as a group that would be interesting things to look at. The first one is to try and understand if there are plant-to-plant interferences. So if power plants upstream and their water use affect downstream power plants, either through using water and evaporating it, or through thermal pollution, so elevating the river temperatures at downstream power plants. Does that have an impact on downstream operations? Is there some kind of connection along river networks that limits power production? That's our first question. The second question was to try and understand where and what are the vulnerability levels of thermoelectric generation to future climate conditions. And the third one is, well, if there are climate water impacts, what does that mean for our planning tools, the planning tools that we're using today, to try and understand what type of infrastructure we need in the future to make sure that our electricity supply meets demand. Because today, these types of tools are used separately. Electricity forecasting tools where we try and simulate future infrastructure and operations is typically done separately without considering any climate water impacts. And then on the other hand, on the other side, when we do try and understand climate water impacts, we use hydrology models or climate models that don't really take into account any changes in infrastructure or grid operation. So there's a miscommunication there when we try and understand the full connection between electricity, water, and climate, and I'll speak about that a little bit as well in the third study. Next. So our first study, the key results and the approach, as well as speak about now, is looking at plant-to-plant interferences. And we picked the Mississippi River watershed because that's where you have the highest number of connections between, potential connections between power plants. We looked at 128 once-through power plants and 198 recirculating power plants in the region. And we looked at their operations on a daily time step between 1995 and 2015, and we focused on summertime electricity generation because that's when you have peak generation, and also that's when your river temperatures are warmest, and you're going to have a higher impact on your once-through power plants. If you click next. So to try and assess and analyze the interferences and power output and any losses associated with climate and water constraints, we developed a power plant simulation tool. And what this tool does is, for every power plant, we are able to look at what the air temperature is, how much water is available for cooling, dependent on the location where the power plant is located along the river. We can look at thermal effluents from the power plant and potential thermal effluents that have come from upstream power plants and have cascaded downstream. And we can analyze this all the way from the headwaters to the basin now. And this power plant simulation model is coupled with a hydrology model. And this hydrology model is what we're using to be able to tell us how much water is actually available at different parts along the river. And if you hit next. So here there's a couple graphics going on, and I'll explain what's happening on the top right map first. On the top right map, we mapped out the thermal pollution levels from the 128 power plants. And the different colors of the rivers show the different magnitudes of thermal pollution, and this is on average. And what we're also able to do with our modeling tool is understand which power plants are affecting one another and which power plants are more vulnerable to upstream thermal pollution and upstream water use. And the way that we analyzed the impact on power production is that we came up with a metric called the adjusted available capacity. And what this means is that if you have a power plant that is, let's say, has a 100 megawatt nameplate, but because of thermal pollution impacts or elevated river temperatures, only 90 megawatts is usable, then this is equal to a 90% AAC, adjusted available capacity, or which is the same thing as saying that there's a 10% loss in available capacity at that power plant. So what we did was we looked at the thermal pollution impacts on the available capacity throughout the whole region. And what we saw was that if you only look at thermal pollution, so the impact of elevated river temperatures because of thermal pollution, on average, you get about a 0.5% loss in available capacity throughout the region at these once-through facilities because of these elevated river temperatures due to thermal pollution. Then if you look at what the impact is due to thermal pollution and upstream water consumption, so evaporation through cooling towers, for example, we see that if you hit next, we see that whoops, you go back on. We see that during the drought conditions of 2007 and 2012, there are peak losses that are associated both with thermal pollution and upstream water consumption, which basically lowers the water that's available at downstream locations and has a higher impact during these drought conditions. So this is looking at plant-to-plant interferences, trying to understand if there are any limitations on power production because of upstream and downstream power plant operations. If you hit next. Now, the next step that we did was we looked at, well, these are the impacts due to the connections within river networks of power plants, but how does this compare to everyday losses in terms of natural air temperatures and water availability at power plants? And what you see was at the top, where you have the pink and the orange, that's the same graph that we saw before, where you have about 0.5% loss in available capacity because of these plant-to-plant interferences. But what this black line shows is the total adjusted available capacity losses. So this is occurring just because air temperatures are naturally too warm, or river temperatures are just naturally too warm, or there isn't enough water. And so, for example, if a power plant's ideal operations are under 20 degrees Celsius for cooling inlet temperatures, for example, during a typical summer, it will go above 20 degrees Celsius and it might reach 25, 30, and that's where you see most of the losses in AAC, and they average at about 8%. And so what this tells us is that, yes, there are interferences between power plants, but the real impact comes from our overall day-to-day climate, and that is more of a limiting factor on ideal operations than the plant-to-plant interferences. If you hit next. So this is just showing you another aspect of what our modeling tools can do. We were able to implement a technology scenario, which is also actually a policy scenario. If we go back and remember that a lot of the once-through cooling systems are now changing to recirculating cooling systems. We looked at and focused on the drought conditions in 2007 and 2012 and said, well, what if all the once-through plants were actually recirculating power plants? How would that affect power production and impacts on our power supply? And what we saw was that because recirculating technologies rely less on water and less on river temperatures, there was an overall gain in available capacity during these drought conditions, even though cooling towers actually take a hit in efficiency because they require more pumping within the power plant itself to move water between the cooling tower and the power plant. We actually saw an overall increase, and that's what these purple circles show. They show the power plants that were actually able to have an increase in available capacity relative to if they were once-through plants, which is what's actually happening on the ground. But what you also see is that along the main stem of the Mississippi River, there are actually losses, and that's because the main stem of the Mississippi River always has enough water for cooling, and the temperatures are typically relatively lower than the upstream watersheds that we see. So it's very important to take into account the region-specific climate and hydrology conditions, as well as the type of technologies that you have when you try and understand vulnerabilities to climate and water. So if you hit next. So understanding that most of the impacts come from day-to-day climate and water impacts, our next question is to try and understand where and what are the vulnerability levels of our future power supply given future climate warming. And so again, we focused on summertime conditions, and we looked at today's climate and a future climate to try and understand what the impacts are going to be. And the map shows 1,080 power plants, which is the power plant infrastructure in 2015. And as we see, there are different types of steam and combined cycle cooling, and that most of the infrastructure is in the eastern U.S., the thermoelectric infrastructure is in the eastern. If you hit next. Now, we used 3 metrics to try and understand vulnerabilities. The first one was what I've spoken about in the previous study, looking at the adjusted available capacity. So relative to the nameplate capacity, how much is available? And then the next 2 metrics we we try to come up with are trying to put the physical impacts in some kind of power systems context. So we're going to look at the probability of meeting peak power output and also the impact on reserve margins across 19 NERC regions. So if you hit next. So this is what the available capacity looks like today. And we see that most of the impacts happen in the southeast, where you have warmer river temperatures and air temperatures, and less impacts in the northeast. But what's interesting is that you see more green in the western interconnection in the southwest. And that's because most of those power plants are combined cycles, which require less water and are less vulnerable to warm air temperatures and water stress. If you hit next. So what we then did, we took today's infrastructure and climate, and we applied temperature and water changes that are projected to happen in the future. If you hit next. And just zooming in here, this shows the changes in condenser inlet temperatures. And what we see is that all over the US, there's a warming. But what's interesting to see is that the magnitude of warming relative to today is higher in the northern parts of the US relative to the southern parts. So that your climate impact is actually going to be greater in the northern regions than the southern regions. However, the southern regions are still warmer than the northern regions, but what we're trying to show is that the climate impacts relative to today might be greater in these northern regions, because that's where you're going to see a higher magnitude of change. If you hit next. So we applied those temperature changes and changes in condenser inlet temperatures onto the infrastructure. And what we saw was that at nearly all power plants, at 99% of the thermoelectric plants in the US, there are losses in available capacity. And at the national level, it's equal to about a 2.5% drop in available capacity. But what's important to note is that there's a huge range in terms of the individual impact, which goes from about negative 30%. So in some power plants, see a minus 30% loss in available capacity, while some actually see an increase. But this is only for a couple of power plants. And again, we see that most of the impacts are in the southeast, and they move northwards because of this increasing condenser inlet temperature magnitude impact on the northern regions. If you hit next. So this showed us what the physical impacts are on the power plants in terms of available capacity. But as we know, we don't need these power plants to operate at 100% capacity, at full capacity 24/7. What's really important is to try and understand if these power plants are going to have enough available capacity to meet our demands. And so when we applied a probability metric to try and understand, well, under future conditions, given these climate water impacts, what's the probability of meeting peak demand? And what we saw was that even though at the most vulnerable plants, and by most vulnerable, we took all the power plants that have 90% or less adjusted available capacity, which means a 10% loss or more of available capacity, and there's 165 of these power plants. Well, we saw that about half of these power plants still have a greater than 50% chance of meeting their peak demands. And we also see that there's a lot of blues, which means a high probability of meeting your peak demand on any given day in the southeast. So what this tells us is that it's very important to connect our planning tools that we're using to try and understand climate and water impacts on our power sector. We can't just use hydrology or climate models or just energy forecasting models. We really have to bring these together to try and better understand our system vulnerabilities to future climate. If you hit next. So what we also did was try to understand the impacts on reserve margins. Now this is only looking at thermoelectric reserve margins, and the black dots are the ideal reserve margins. So where the reserve margins would be relative to no climate and water impacts. And by reserve margins, in this case, I mean the total available capacity relative to your peak demand in 2015. And so what we see is that even though there's a reduction in your power supply reliability in these reserve margins, all reserve margins are still positive, which shows us that there's enough capacity in the system today to alleviate and neutralize any climate water impacts. So there's enough capacity to do that. Now, there might be additional impacts to that, including increased production costs potentially. But what we're seeing is that overall, you have positive reserve margins. Now, another thing to note is that the Western interconnection sees at most a 4% reduction because of climate change, whereas the Eastern interconnection sees a 7% reduction. And that's because, as I mentioned before, the Western interconnection relies a lot more on natural gas combined cycle plants, which need less water and are less vulnerable to warmer temperatures and water stress compared to the Eastern interconnection. If you hit next. So just quickly, the key takeaways from that was that, yes, there are climate and water impacts, and they are going to affect almost all power plants in the US, thermoelectric plants, and that it's important to look at the different regional impacts because we have different types of river characteristics, different types of climate characteristics, and different power plant technologies. And these are all important to take into consideration when we try and understand vulnerabilities to future climate. And we saw that without a power systems context, without looking at the probabilities of meeting peak demand, we might overstate the extent of the system's vulnerabilities. Or we might not understand where exactly the vulnerabilities are without putting the climate and water impacts, the physical impacts, into a power systems context. But was that study good enough to fully and holistically address the power sector's vulnerability? And the answer is no. And that's because we didn't take into account what the future infrastructure might look like, because we're going to have a change in infrastructure as power plants are retired and as we need more capacity to come online to meet future electric loads, future demands. And we're going to have different potential pathways of the future infrastructure. We might have more renewables, or we might remain reliant on coal, for example. And if you hit next. So what we see now is that, given our understanding that there are physical climate water impacts and vulnerabilities at thermoelectric plants, and the need to understand what the future infrastructure is going to look like, what we've done now is we've taken an energy forecasting modeling tool, which was developed at Ariel, and what the model is able to do is look at different growth scenarios under economic and technology assumptions and policy assumptions, and it gives the least cost infrastructure build out that's required in order for supply to meet demand. And it represents all types of generators, including thermoelectric and renewable and battery storage and all of the above. What it's also able to do is capture the climate impacts on future demand. So as we have more cooling degree days, so days in which we need more space cooling, we need to turn on our air conditioning more, we're going to have an increase in demand for electricity. And so we're going to need to build more capacity in order to meet that demand. If you hit next. So what we looked at was 4 different infrastructure pathway options. A business as usual, which just says if things were to continue as they are today with prices and markets and no new policies, what would the infrastructure look like? The second scenario was a carbon emission reduction scenario, where we're trying to achieve an 80% carbon reduction by 2050 relative to 2005 levels. And then the second carbon emission reduction was to try and get at a lower carbon infrastructure in a different way. And to do that, we raised the wind and solar cost assumptions. And we also extended the lifetime for nuclear power plants as they're low carbon, and we gave them a second license extension. And it has the same goal of reaching the 80% carbon reduction by 2050. And then our fourth scenario was a continued reliance on coal scenario. And in order to do that, we said you have to maintain coal operating costs as low, and you have to extend the lifetime for coal power plants. So there were no coal-based retirements under that scenario. So we took these 4 energy scenarios, And if you hit next, we fed the electricity capacity and generation projections into our power plant simulation model, which we used in the previous two studies. And if you hit next, what we tried to understand was we take the anticipated reliability that our energy forecasting modeling tool is saying, and we tried to see if it's equal to the reliability once you take into consideration climate and water change impacts. And if the two are equal, then that's great. And our infrastructure forecast from the REED model, which is the energy forecasting model, it means that everything's feasible in terms of climate, water, and the economic perspective. But if reliability standards are not met, then we have to create a data exchange platform where we take the constraints on power plants and we give them back as constraints into the energy forecasting tool so that we can recalculate what the future infrastructure will be in order to adapt and consider climate water change impacts so that we can meet our anticipated and ideal reliability standards while taking into consideration climate and water impacts. And this type of tool is new because so far what we've done typically is we've used the modeling tools separately. We've used the energy forecasting tool on its own to try and find the least cost solution for future infrastructure, but without really taking into account climate and water impacts on generation or what increases in demand might look like. On the other hand, we've had these studies that have used hydrology and climate models and impacts on power plants, but they've not really taken into consideration future infrastructure and what this looks like. And so our planning tools have been siloed and separate, and this is us trying to bring them together so that we can better understand what our future infrastructure might need to look like under a warmer climate. If you hit next. So we see that under future climate, because of increases in electricity needs, because of space cooling, there's a 46% increase in capacity. And so we see that relative to today, you have different levels of capacity builds in the future in order to meet this demand. And this demand is constant across all the scenarios. And what we see is that under the carbon emission reduction 1, which has high renewables, it has the most capacity build. And the reason for that is because of the variability of renewables. You also need, as well as renewables, you also need gas turbines and combined cycle plants that have sufficient ramping rates during peak demand to be able to help meet peak demand. And there's the least amount of build under the continued coal scenario because it's taking advantage of existing coal power plants. And if you hit next. This is again looking at the adjusted available capacity. And what's interesting here is that relative to what we saw in the previous study, adjusted available capacity actually improves through time. And that's because more renewables come online, and as our less efficient and more water and climate vulnerable power plants such as coal and nuclear retire, there's actually an improvement in our available capacity. And if you hit next again, we see that there's a regional difference in this. So for example, in the Western interconnection, there's actually a decrease. And the reason for that is that some climate adaptation measures have already been taken because so much of the capacity is already natural gas-based. They're already minimizing the climate water impacts. And ERCOT, which is Texas, we see it remain relatively the same, but the real impact is in the Eastern interconnection. And because there's so much capacity in the Eastern interconnection, this trend is reflected at the national level. And this is where we see the improvement in AAC as older thermoelectric plants retire. And but in the coal scenario, we see it remain relatively the same despite any new or more efficient combined cycle and renewables coming online. If you hit next. Here we see the impacts on reserve margins. And we see that there's a decrease in oil reserve margins. If you hit next again, we see that this shows us all the NERC regions, and as renewables increase, the impact on reserve margins has decreased. And if you hit next, we see that, I'm just going to point out here as we're running out of time, that the circ region, the colors show the minimum reserve margin between 2020 and 2050 relative to what our energy forecasting modeling tool is saying. And the reason I'm pointing out the circ region, is the red dots, is because we have a negative reserve margin. And so what that's telling us is that the forecasting tool that we're using is actually coming up with an infeasible solution in the context of climate and water impacts. And although it might not mean that you have a blackout, it does mean an infeasible solution in terms of future infrastructure, because the model is saying that we have enough capacity to meet demand, but once you take climate and water impacts into account, we see that it doesn't. So if you hit next, we see that we have to go and loop through the models in order to adjust the infrastructure to get the correct infrastructure that is reliable under climate and water changes. If you hit next again, we see that there are, to compensate for climate and water impacts, you have to build more capacity. And the capacity that's built is mainly combustion turbines, so that we have sufficient ramping rates and capacity during peak demand, and also renewables. And then if you hit next, we see that the change in power output and dispatch decisions means that we dispatch less steam cycle plants, so your coal and your nuclear, there's less of that, and even less combined cycle natural gas plants. But you have a lot more renewables that are now dispatched because you have this additional capacity, and combustion turbine as well. And this impact on infrastructure is pretty substantial. If you look at the bottom right bar chart, there's a 10 to 30% increase in our capacity needs once we take into account climate and water impact. So if we want an infrastructure that's adaptable to a future climate, we really do have to increase the amount of capacity that we have to maintain the reliability standards that we aimed for in the forecasting tool. If you hit next. And this is just to show that there's a regional difference, and because we're running out of time, we could just keep going. And this is just summarizing that study to say that there is a substantial impact on, once we take climate and water impacts into account, there's a substantial impact on our modeling tools. It's important to, as adaptation measures, to take into account the connectivity of regional power systems, because generation shifts from more vulnerable to less vulnerable regions, and there's more renewable generation coming online as well. If you hit next. And so this is kind of the last slide, just to remind everyone, as I mentioned at the beginning, that we're coming to the final stages of our project. And what I've shown up to now is our internal thinking and scenario building. And what we want to know is, are the tools that we're building helpful? How can we make them more helpful? What kind of scenarios is everyone interested in and are realistic? And our approach is, over the next few months, is going to be one-on-one meetings with interested decision makers, engage in a dialogue, and try and create some modeling experiments. And then we're going to have a workshop late spring of next year in which we unveil some of these results and have a discussion on climate, water, energy connections. And that's it.
That's great. Thank you. I'm going to introduce Emily Gruber. She's a civil engineer and environmental sociologist with the Georgia Institute of Technology. And she's been studying how community and societal priorities can be incorporated using policy and project excuse me, related to energy, water, and infrastructure systems. Emily, you have any thoughts?
Yeah, thank you. And thank you for the opportunity to both see some of this work coming out and to comment a little bit on it. As Mariana mentioned, I work a lot on energy, water, nexus systems and kind of decision-making contexts. And one of the things that I think is really exciting about this study in particular is the focus on particular power plants and particular river systems. One of the things that Ariel was talking about, just in terms of localized impacts on power plants because of water resources, is also something that's coming up a lot in the hydroelectricity analysis community. And I think one of the really interesting ways that this work might get used is kind of trying to put together some of these insights about thermoelectric power plants with some of what people have been realizing about the hydro system. I think in looking at this work on the thermoelectric power system, Ariel mentioned a couple of times that we are expecting to see some fairly significant changes to power plant availability because of things like water temperature and droughts. And I think what we've seen on the hydro side too is that due to droughts and due to things like that, you can see really, really significant impacts on the amount of hydro that's available. So I spent a lot of the last few years in California. Over a 5-year period, we saw the hydro output actually drop by about 70% because of drought and things like that. And so the availability of this study looking specifically at thermo, combining with that, I think can be a really, really useful way to look at what we actually expect to see unfold as different hydrologic scenarios kind of spin out over time. I think one of the other really interesting things that came out of Ariel's presentation is just thinking about the value of thermal power plants as renewable backup. We see a lot of discussion about how much thermoelectric we actually need to keep in place in order to kind of keep reliability up on the grid. I think understanding what the water impacts of climate change and some future hydrologic patterns are, especially in this very high spatial resolution way, are going to go a long way for helping us understand what that actually looks like in terms of how much thermal backup you actually need. I think also, as was brought up a couple times during the main presentation, this is going to be a really interesting way to kind of think about what future renewable capacity might look like. So as we see more renewable capacity coming online, it's likely that which renewables come online is going to matter quite a bit in the water sense. If you see a bunch of wind or solar, you probably don't see much of a water impact. And as those take over for some of our more conventional water using power plants, we probably expect to see water freed up. You see a lot of biomass power plants, and particularly in the Southeast, where thermoelectric is already threatened, that might be a very different picture. So thinking about how those kinds of scenarios might be analyzed with some of this work, I think is also really interesting. One question that I would like to put back to Ariel and the team is if you could talk a little bit about seasonality impacts, because I think one of the other things that came out during your presentation is that as we see temperature constraints and as we see some water availability constraints spinning through, that's probably going to interact quite a bit with when we have higher or different electricity use patterns, particularly in the summertime. And I'm curious whether some of the spatial specificity that you have can be combined with anything temporal to really start talking about those seasonality issues in a directed way.
Yeah, that's a great question. So our modeling looked at was at a daily time step, and what we saw was that that most of the impacts really occur between May and September. So during the winter months, your electricity demand is much lower, and your available capacity, even though freezing conditions might affect it, the impact is really minimal, and that's why we focused on summertime, when your electricity demand is at its peak, when your air temperatures are the warmest, when your river temperatures are the warmest, and you also have less available water during that time.
Yeah, great. I think that that's a really, really important data set to have for the community. So thank you for doing the work. But yeah, overall, I think I'll just close to the broader panel by just commenting that it's really great to see so much more work actually focusing on water impacts on these systems, because we know that a lot of multi-criteria decisions have to get made about water systems. I think the hydro community has been very aware of this for a while, that you're balancing irrigation needs with power needs versus recreational needs and things like that. And as we recognize that it's not just the hydro system, but actually the whole power system that starts to need to think about some of these issues a little bit more holistically and a little bit more directly, it's a really great opportunity for understanding what our power systems are going to look like into the future. So thank you.
I found it very interesting, in the Northeast, looking at the maps of how really constrained it is versus the South, which you intuitively think would be the other way around because of the seasonality. But it would be interesting to see is in New Jersey in particular, we're taking Oyster Creek nuclear power plant offline, but we have a solicitation out for 1,100 megawatts of offshore wind. And then at the same time, well, you're sort of replacing your capacity, you're then also introducing another element which is being pushed, well, nationally, which is electrification of the transportation industry. And I wonder if you had factored any of these new large electric needs into your study.
Yeah, that's a great point. We actually haven't considered any transportation scenarios or electrification of the power grid, but it's something that we could certainly look into. Another thing just to note in terms of the regional impacts is that as some regions become more vulnerable and more affected by climate and water, like the Southeast, for example, when we did our modeling experiments and we looked at how the infrastructure might change in order to become more adaptive to future climate and water, we saw that the northern parts of the US that now, for example, might rely on imports from the Southeast, actually it's more economic for them to build capacity in their own regions so that they're less vulnerable to climate water impacts and the imports from the more vulnerable regions.
Interesting. So as a regulator, what sort of policy or sort of market obstacles do you see for trying to get a closer relationship between energy, drinking water, and wastewater utilities?
I'm not quite sure how to answer that.
In your study,
I'm not a regulator.
Well, we have quite a few regulators on the call. We come up with, well, how do we get to the next step, and how do we, implement some of these things, or how they made useful? Are there any obstacles for, greater, working together? I mean, this last year at NARUC was the first time we really took a close look at, instead of just saying the water energy nexus, that they were absolutely intertwined. You can't have one without the other. And are there any obstacles that you see for not being able to keep this closeness, this relationship together?
So this is Jordan Macknick. I can chime in here on this topic. I think this is going to be an ongoing theme, I think, throughout the rest of the webinars as well. But I think there is a fundamental challenge in how you get different types of regulators to talk to each other to ensure that the regulations that are put forth, whether it's addressing the wastewater sector or water, drinking water, or the power sector, are not working against each other and do not prevent innovation and do not prevent cost-effective decisions that would also lead to environmental benefits from being implemented. And I think, unfortunately, one of the challenges is that many times these entities are not speaking with each other, and in the past, some of that has been of a result of us not really having the right sorts of modeling tools or the right technical capabilities to look at a comprehensive suite of energy and environment and water-related issues all in one platform. And I think some of the work that Ariel was discussing and the work that he has done is really showing that we're sort of entering a new age where we can address a lot of these issues in a very comprehensive and holistic manner. And so I think we have the tools to do this, and so hopefully we can increase this dialogue and make sure we get the right people in the room, the right decision makers in the room, who are also bringing with them this sort of holistic and comprehensive perspective as well.
I think it's a great start because we have many deregulated states, so we don't have control over generation, and the other is that there's so many fragmented water systems and water sources, or there may be a source that has several systems on it. Some may be regulated, some may not be. This is a more complex issue than, you've made it look really simple here, but it certainly is not. I want to know, Carrie, do we have any questions from anyone in the audience?
I am not seeing any questions coming in from the audience.
Okay. Is Dr. Tidwell still on?
I am here.
Oh, any thoughts? for going forward?
Absolutely. I mean, I agree with all of Emily's comments. It's great to see, as I think Ariel's pointed out, this real trying to draw a connection with the tools and the expertise of both the water and the energy management and bringing them together. And that's been part of my experience in working with WEC and ERCOT and EPIC to some extent in integrating water into their long-term transmission planning. They're very aware of water and some of the basic issues, the way it relates to the energy system, but there are a lot of other details in terms of the broader system, the regulations and such that that has been important to them for us to interact with them. So I think that's, and vice versa, how much we learn about the electric system and its nuances and how that plays into the interaction with the water. So it's very important. I think one of the important kind of steps forward that we take is having these kinds of interactions and case studies, and where we do bring the water managers and the energy managers together to do planning. And I would argue that one of the next steps is with the regulators as well. And I think that's what kind of Ariel has put on the table here is an opportunity to start some of that through the end of this project. And so we can get some of those different voices together. Just one other thing that struck me, and I'm not quite sure, I think it would be valuable to understand kind of the, you showed what looked to be some pretty important potential demands and growth to meet peak climate future conditions. And so in the context of what, if you didn't have the climate, you weren't worried about the water, how much extra peaking capacity are we talking about? And then one thought there, because that to me would be a really important result that would really drive the way we think about the future, because those are real dollars. And to what extent might the demand side management become really important, or even storage in the system, and how that might offset some of those big, look like some pretty significant increases to meet those peak demands.
Yeah, so the peak demands were that 46% increase that we saw was because of increased cooling space needs, so turning on your air conditioners, and as well as population growth. And so there's an increase in infrastructure and capacity in order to meet those demands. But then on top of that, if we take into account climate and water impacts on the generation side, we then need an additional 10 to 30%, depending on the energy scenario that we saw, an additional 10 to 30% on top of that to compensate for the climate water impacts on generation. So without that additional infrastructure, what we're seeing is that your ideal reliability standards might not be met.
Yeah, I mean that's very significant. I'm just wondering then the opportunities either for storage in the system. I don't know to what extent that, whether, I guess, for that kind of peaking, whether that would play in, and then the demand side management, to what extent, because I mean that 10 to 30%, that's a pretty big lift there, I would think, in terms of cost to the utilities, just to and you know what the I mean, how often that spare capacity would be necessary, right? So that would help you decide maybe are there some other alternatives we could take to help offset some of that growth in the peaking reserve.
Yeah, so in terms of the scenarios that we looked at, under the current market conditions, in terms of storage, like battery storage, it was actually more economic to build gas turbines to come on during peaking rather than have battery storage or anything like that. Now, in terms of demand response, I think that there are different options for that. I think Jordan might be able to, he's done a little bit of work on that, so might be able to share something.
Yeah, and I think to really address that question, there are different types of demand response resources, that can provide different types of services and can operate at different timescales. But I think that brings up another point, is that would take a different suite of models, which is what we'd have to do to look at that, is to use a much finer and higher resolution operations modeling framework to look at how those demand response resources could be best used and how they might coincide with some of these water and climate related vulnerabilities. It's a subject of some ongoing research that we're doing right now, that NREL is doing also in conjunction with Pacific Northwest and Sandia National Laboratories.
Terrific. Well, I look forward to continued research in this area, and I will turn this back over to Carrie Worthington.
Thank you all so much for your time today, and we really appreciate all the comments that were made. The materials will be on the NARUC website on the Center for Partnerships and Innovation webpage, and please join us on the 17th for the final Water and Thermoelectric Energy Water Nexus webinar series. Thank you. Bye.